When a chemical reaction occurs, the actual nucleus of the elements don't actually participate in the chemical reaction. It actually is the electrons that actually do most of the chemistry in these reactions. Now, in order to fully understand a chemical equation or how an element is actually going to work in a chemical reaction, you need to understand how the electrons of this atom. Now, initially, when chemists thought of an atom, they actually thought that the electrons were actually a giant ball. They actually were just flying around willy-nilly. There's no rhyme or reason. However, around the turn of the century, they actually found out that the elements are actually more like an onion. They actually have different layers that specific elements are actually in. They're actually termed quantized. So that's what birthed quantum mechanics. So you're getting a little intro into what quantum mechanics are. So in an element, as you're adding more and more electrons, you're filling up all these shells. So while, like for instance, lithium has basically a very small onion, you go down to francium, it's a very huge kind of onion. It has many, many, many shells. Now, each of these layers of the element or the onion actually is composed of 4 different subshells. The S, the P, the D, and the F. Now, each of these subshells contains different amount of orbitals. If you look in your book, you can actually find what these orbitals look like. But to save time, we're just going to move forward. Each orbital has a defined number of subshell has a defined number of orbitals in them. So S has 1, P has 3, D has 5, and F has 7 orbitals. Now, for each orbital, it can hold 2 electrons. So the S holds 2 electrons, the P holds 6 electrons, the D holds 10 electrons, and the F holds 14 electrons. Now, if you look at the periodic table, you actually can see the first 2 columns are basically the S orbitals. The transition metals are the D orbitals, or their last orbitals are the D. The nonmetals are the P orbitals, and lanthanized down here are the F orbitals. Now, this chart is in every chemistry textbook. What it actually shows is how you fill up the shells. They're at each subshell is at a slightly different energy level, and they get filled in a specific order. So, for instance, the 1s gets filled up before the 3s. So if you have 4 electrons, 2 go in the 1s, 2 go in the 2s, and so forth and so on. To better understand this, let's look at these 2 elements, carbon and iron. Now, carbon has 6 electrons. Its electron configuration, so 2 are going to go in the first s level, 2s, 2, and then we have 2 electrons left over, so we have a partially filled P subshell as 2p2. Now, iron's a little bit more complicated. Iron has 26 electrons. So you go back to that table and just keep filling in the elements until you're completely full. So it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 comes before the 3d6. So if you add all these up, it should total 26. Now, you can see how if you're going down to the farther, the heavier atoms, you can get more and more electrons. However, there's a shortcut method. So, for instance, in iron, the core electrons, or 1s up through the 3p6, actually is what can be shorthand written as the nearest a noble gas. So argon here actually represents the 1s2 to the 3p6. So you can just write argon 4s2 3d6. Now, try this practice problem. Find the electronic configuration of iridium. We'll go through this when we come back. All right, iridium has 77 electrons. Now we go back to that chart I spoke of earlier and just keep adding until you go. So bear with me on this one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and we actually go into the F block, 4f, 14, then finally 5d7. That's the long way to write it. You can also just write it xenon. So it goes, all this column up here represents the electron configuration of xenon. So shorthand, just write xenon, 6s2, 4f, 14, 5d7.